So in this second example, um, it's more complicated than the first example uh, by a couple of issues. Um, so the situation of this problem is there's a person on top of a building. They're up above the ground by, it looks like 125 meters from top to bottom. And they have taken a rock and they have thrown it upwards. So they throw the rock up at 20 meters per second, and that's when the clock starts on the stopwatch. So this is the initial velocity, is upwards at 20 meters per second. After they throw it, the rock is considered to be in free fall. And all it's going to do is, on the way up, it slows down, reaches some highest point, and then speeds up faster, 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 all the way down past a person I'm going to refer to as person P. So here is a person, I'll just call them P. So the rock is going to go past person P and then continue to speed up all the way down to the ground. When does the rock pass P? So the first question is, what time T? How much time do you need to wait before the rock goes up to the top and then comes down and passes P on the way down? So that's the first question. When does the rock pass P? And then the second question is, what is the velocity of the rock when it finally gets to the ground and is moving really, really fast? So there's two questions here. The second question is interesting because depending on how you want to solve it, I'll show you a simple way to solve it that takes a long time. And then I'm going to refer you to a really interesting relationship that solves this problem in one step. Okay, but first things first, when does the rock pass P? So let's go down here and start to study this problem. So like in the previous problem, I don't really know how to start, but I do know that I want to use, or that I am allowed to use, this generic form for the position as a function of time. And the reason is because it is a free fall problem. So even though the rock was not dropped from rest, it was actually thrown up into the air, I get to use this because even a rock thrown up into the air is considered in free fall. Okay, so problem is, or you remember from the previous example, that in order to fill in values, to actually use this formula, I need to decide on what plus or minus to put in front of 9.8 meters per second squared. I got to figure out, do I put in initial velocity is positive or negative? And also, I don't know what y sub 0 is. So all of those are addressed, or decisions on how to put these values in are addressed by the choice of coordinate system. So coordinate system, let's make some choices, and I'm going to make choices that are different than the choices I made before. So just for fun. So before I said up was positive, I'm going to say down is positive. And before I put y equals to 0 at the top of the cliff, I'm going to put y equals to 0 at the person P. So person P is at y equals to 0. Yeah, and then also, you remember I did describe that we needed to choose when t equals to 0. T equals to 0 is just going to be right at the start of the problem. So the ball will start on the way up at t equals to 0, go up to some high place a little bit later, turn around and come down right through the same place even later. Even later than that it's at P, and then even later than that it's at the ground. But yeah, so t equals to 0 is actually already described in the problem. But down is positive, and the person P is at y equals to 0. So this is y equals to 0. So once I've chosen those coordinate system details, y sub 0 is, so down is positive, so that means up is negative. So this is position negative 50 meters. Negative 50 meters. down is positive, I'm going to go ahead and go straight to the acceleration. Since down is positive, the acceleration in the y direction, down is the positive direction, so I take the plus 9.8 meters per second squared. And because down is positive and the initial velocity is upwards, this up at 20 meters per second indicates that actually the initial velocity is a negative 20 meters per second. These are the details, and I can go now and fill in my generic form. Y of t equals to negative 50 meters minus 20 meters per second t times t plus 1/2 of 9.8 meters per second squared t squared, like this. And this is now my position as a function of time. If I want, I can take the derivative, understand the velocity, which may be useful in that second question. But the question of when does the rock pass P, that question is simply answered at what special time t star is the rock at P, but the rock at P is y equals to 0. So I want to know when is y equals to 0. I hope that it's okay. I'm not going to solve this problem. You can solve this problem yourself. You'll just put in 0 on the left-hand side of this formula. So 0 equals all this stuff. And then you're going to do the quadratic formula. What I will show you is something interesting about using the quadratic formula in this case. So I'm just going to copy this. Y of t is negative 50 meters, not plus, but minus 20 meters per second t, and then plus, so 9.8 over 2 is 4.9, so I'm just going to go ahead and evaluate that 4.9. And I am looking for the special time when this expression is 0. So it's set up really nicely for me to do the quadratic formula. I think it's really good practice for you to go back and review quadratic formula, but I'm not going to spend pedantic time on the use of it in this case. I'll let you go and figure out why I'm allowed to write what I'm about to write. So it turns out that t star is equal to 20 meters per second plus or minus the square root of 20 meters per second squared minus 4 times negative 50 meters times 4.9 meters per second squared, all divided by 2 times 4.9 meters per second squared. Okay, if you remember, the solution to ax squared plus bx plus c equals to 0 is x equals the opposite of b plus or minus the square root b squared minus 4ac, all divided by 2a. So that's what I've done over here. But the thing I wanted to show you is how do the units work out. So watch this. I've got a term here, meters per second, and I'm adding or subtracting it, right? Because there's 2 answers to this quadratic problem, or in general 2 answers, or possibly 2 answers, excuse me. So plus or minus the square root of this stuff. The first term inside of the square root is going to be 20 meters per second times 20 meters per second. So the units of this thing inside the square root is meters squared per second squared. Meters times meters divided by second squared. The second term in there is also meters squared per second squared. The square root of meters squared per second squared is also meters per second. So the entire top is all meters per second. The bottom is meters per second squared. So the top is meters per second, the bottom is meters per second squared. this is equal to meters over seconds times the inverse of the lower, so second squared over meter, and this is the second. And the reason I think that's important is because I just used this weird, crazy quadratic formula, but the quadratic formula does the right thing with the dimensions and the units. So I am solving for a time, and I better have units of seconds. And so, yeah, out pops a second.